In 1998, LeNet-5 established a new approach to computer vision using spatial hierarchies. Moving beyond flat multi-layer perceptrons, we use a design built on 3D convolutional blocks, labeled here from C1 to S4, to extract features before the fully connected classifying layers. Our goal is to apply this architecture to the MNIST dataset to categorize a grid of raw, handwritten digits. To manage an architecture with this many layers, we have to establish a reproducible environment before we write the first line of model code. We begin by initializing manual seeds for the random number generators in NumPy and PyTorch to ensure our training run is replicable. We also use a training config data class to direct execution to either the CPU or the GPU. By locking these configurations, we ensure any improvements in our metrics are the direct result of architectural choices rather than hardware or initialization noise. Standard MNIST images are 28 pixels square. We have to resize them to the 32 by 32 dimensions required by LeNet-5. PyTorch expects a specific input order, so we transpose dimensions from height, width, channel to channel, height, width. To keep values consistent, we apply a normalization equation across each channel, subtracting the mean and dividing by the standard deviation. For MNIST, these constants are a mean of 0.1307 and a standard deviation of 0.3081. Standardizing the data range in this way helps stabilize the training process, preventing the network from assigning excessive weight to unscaled pixel values. In this implementation, we divide the network into two distinct modules, a convolutional body for feature extraction and a fully connected head for the final classification. When connecting these modules, the in channels of a layer must match the out channels of the layer that came before it to ensure the data flows without dimension errors. Each 2D convolutional layer is defined by three parameters: the kernel size for filter dimensions, padding at image edges, and stride that determines how the filter steps across pixels. There is no activation function after the final linear layer. This allows the model to output raw logits, converted into probabilities using a softmax function during inference. By encapsulating the layers into these discrete blocks, we can more easily test or swap specific parts of the feature extractor without rewriting the entire model. Training is managed through a 5-step sequence repeated every epoch. First, move data to the device. Second, execute a forward pass. Third, calculate loss using the cross-entropy function. Fourth, find gradients using the backward function. Fifth, use the optimizer to update the weights. Pause the video for a moment and see if you can recall those 5 steps in order. When saving your work, you can store the model.stateDict for future predictions. However, if you want to resume training later, you also need to save the optimizer.stateDict to preserve your learning rate and progress. This 5-step logic provides the basic framework for managing weight updates and loss calculation in our classification task. These plots show our progress across 20 epochs, tracking both the accuracy and the loss for the training and validation sets. The blue validation curve climbs steadily before leveling off near 1.0, suggesting the model successfully learned the features of the handwritten digits. On the final test set, the model achieved an accuracy of 0.9876 with a loss of 0.0381. We can see this in practice by reviewing a batch of predictions, where the model correctly identifies the target labels for most images. Even here, mistakes happen. Look at the red label. A poorly formed 2 led to an incorrect prediction of 3. By combining consistent data preparation, a modular architecture, and a standard training loop, we've used this historical design to reach nearly 99% accuracy on MNIST.